It's my pleasure, of course, to introduce Martin Plenio. I've worked with Martin for over a decade now. So a bit about him. Martin did his PhD from Göttingen, the birthplace of quantum mechanics. After that, he was at Imperial College in London as a professor. And in 2009, Germany managed to bring him back through the Alexander von Humboldt professorship as one of the first Alexander von Humboldt professors. And since then, he's been a professor at Ulm and also the co-founder of 2 companies based in Ulm in the south of Germany. And Martin has been awarded many, many prizes. It's a very long list, so I don't want to take too much time, but I do want to mention some numbers. Martin is one of the most highly cited researchers in the world in quantum information and quantum technologies. He has an H index of over 131, and I find it really remarkable that over 120 publications from his side are in Nature, Science, as well as PRL. And he's been a great mentor to many PhDs and postdocs, myself included. There's been over 100 PhDs and postdocs that Martin has mentored, and almost half of them are in very senior positions in academia as well as in the quantum technology industry. So that's also a very big contribution from Martin. In terms of technical fields, he's worked on many, many fields and actually started several fields within quantum, including quantum information, quantum biology, NV Center, quantum computing, and now also contributing to startups. So Martin is the co-founder of QC Design, our startup, as well as Envision Imaging, working on MRI, that's quantum enhanced. And Envision is now at over 150 people, and the product is on the market. And now Martin is supporting QC Design as co-founder and scientific advisor. And of course, for us, it's a great pleasure to learn from Martin and build with Martin. So, all right, with that, I'll pass it on to Martin.
Okay, thank you very much, Ish. Welcome, everybody. It's really a great pleasure to be here and to present the work of QC Design and this wonderful team. And this is really, Plaquette is the main output that we are looking at today. And this is a design and simulation framework that really enables hardware makers to make hardware-aware design of fault-tolerant quantum computers. And in the following slides, following half hour or so, based mostly on the paper that you see here on the front page that we have just posted on the archive, I would like to explain to you some of the key points of Plaquette, what is underlying it, what are its advantages, and I will also show you some applications. Right, so let's get started. And of course, we all know that constructing a fault-tolerant quantum computer is a wonderful endeavor of scientists worldwide, and I'm really confident that it will happen. But it is also a very challenging task, because we have to really work with error-prone physical qubits that maybe have error rates of 10 to the minus 4 or something like that. And we have to build from those logical qubits that have error rates that are as low as error rates of classical information in today's classical computers. So 10 to the minus 15, 10 to the minus 18, or something like that. And that's only possible by using quantum error correction, of course. And that means that we will have to take quantum information, we have to distribute it across millions of physical qubits. We have to orchestrate complex web of physical interactions between those qubits to really delocalize the quantum information so that it becomes robust. But in addition, we have to, of course, also read out a subset of those qubits. We have to decode, we have to interpret these readouts so that we are able to then implement a coherent feedback that removes errors from the system. And that is really a challenging task that requires really design software and design tools, just as we need design tools for today's classical microchips, which are in fact even more complex at the moment than quantum computers, but just contains so many components that a human itself without design tools cannot progress. Okay, so That's sort of the starting point. And we know that this must be possible because there are threshold theorems. That means we know that if we design the right sort of code and we make it larger and larger and larger, and if the error rate is small enough, then under certain error models at least, there is a threshold. That means that when we make the code larger and larger, the error rate goes down. Now, these theorems are really wonderful. They're a great achievement. But of course, they are really valid for very specific error models, typically. I mean, for example, Pauli errors. And that's perfectly fine. They also typically only predict the existence of a threshold, but maybe not the precise location of this threshold, especially not under realistic physical noise. And so really what we need as a quantum computing industry, or as a hardware team in the quantum computing industry, we have something quite different. We don't have this idealized noise model. We have real noise, real world noise. We have leakage, scattering, heating, crosstalk, detuning, gate times, all sorts of things. And many of them do not immediately fit into this idealized setting under which a threshold theorem has been proven. But it is under these real world models that we want to actually determine logical performance. And so this is an important goal that needs to be achieved to make hardware teams able to design quantum computers. So what we need to do, therefore, is we need to be able to take these hardware parameters, combine them with some simulation tool that can predict for real-world errors the logical performance of the system. And once we have the logical performance, then of course we can change physical parameters, we can observe how logical performance changes, and we can actually then learn from this how we might improve the design of our computer. Okay. So you would say, well, okay, fine, why not doing this right now? And of course, we can do this to some extent. There's a host of existing open source tools that address specific aspects of this challenge. But the problem, of course, here is that these are all wonderful tools, but they're often designed for a special purpose. They might not actually be compatible with each other. Interoperability between the tools might be tricky and might require a lot of effort to achieve, an effort that you should not really want, that the hardware team should not really have to do. And also, perhaps many of these tools, not all, but many, might be restricted to specific error models and may really be a little bit far away in some instances from the real-world error models that you have in a real-world hardware. And of course, they have also been designed often for specific computational modes. That means, for example, the circuit model, the measurement-based model, or the fusion-based model. And so what Plaquette is really changing is different things. So firstly, of course, it integrates what is there already. If there are wonderful tools, very strong simulation tools, it is part of Plaquette as a back end, and in a way that is now mutually compatible and it's easy to use. But more important than that, Plaquette also adds new tools. And in particular, it really creates hardware-agnostic simulation methods for real-world error models. So these might include, amongst other things, leakage, sector dynamics, coherent errors, and so on. And that is important to bring it closer to the hardware reality that we have in quantum computing companies. It's also created in a way that it is really agnostic to the specific FTQC design, so it can treat with a circuit model, measurement-based, fusion-based quantum computing, all in one framework. And so, and why does this matter? Well, I mean, as I said already, I mean, a hardware team should not have to spend a lot of time bringing together tools that might not be really easily compatible. And it should also not be forced to make uncontrolled approximations to its real-world error models so that it fits these tools that are available. And all this is changing with Plaquette. Okay, so this is by way of motivation. There's a roadmap, of course, for today's talk, and I will take you through a few aspects of the problem. Firstly, I want to show you how important it is to actually treat real-world error models. And then I will go through the workflow, and I show you also real-world application examples from superconducting qubits, from neutral atoms, and from trapped ions. Okay. So errors in the real world are not Pauli errors, typically. Pauli errors can also take place. Dephasing is an example, of course, but many other errors are not of this form. I mean, there's leakage, where you leave the logical subspace to additional levels. Quantum computers are controlled by control fields. Their intensity may change. The qubit might not sit exactly at the place that you expect, and so therefore, often you may have a small over or under rotation of your qubit. Again, this is something that is not directly a Pauli error. In many atomic settings, Rydberg atoms, ions, you may actually have scattering, where you leave again, you might intermittently leave your Hilbert space, you might scatter, you might incur errors. This has to be taken into account. Ion traps might experience heating, so your environment may actually change in time as well. And all these things are errors that happen in the real world. And we need to be able to treat them as well as possible to give the best advice and simulation tools to the hardware makers. Okay. Now, let me just present a tool that is new, that is part of Plaquette, and that really addresses one of the important challenges in this framework, and that is that of leakage, and also changing environments. So here you can see that we have a qubit subspace that's in green. So that's the, let's say, level 0 and 1. And here you really want to preserve coherence. And you want to represent coherence, and it should build up, because this is really what makes the quantum computer powerful. But of course, what can happen is that you might have leakage to other levels outside of this qubit manifold. These are in pink, let's say, above levels 2 and 3 and so on. And this can happen. And this is something that we need to represent. It's not automatically included in the Clifford algorithms for in the qubit space. And furthermore, also the environment may change. It may well be the case that during the computation, the environment changes. And this is something that we also would like to be able to track and progress. And this is indicated by this bluish additional degree of freedom on the right-hand side. So that's really a tensor product degree of freedom. It's in a different and another Hilbert space. And in that Hilbert space, we describe also environmental dynamics in a simplified way. And the key point here in XPauli is that we want to treat these kind of errors as accurately as possible without incurring the cost of an exponentially growing Hilbert space or exponentially growing computation time. And to this end, we treat the dynamics in the computational subspace using stabilizer formalism and preserving quantum coherence. But in the leaked levels and in the environmental sectors, we keep track of them as classical labels. There might be transitions between the classical labels, but we do not track the coherence, because that would very quickly lead to a rapidly growing computational effort. And so in that sense, we try to keep as much as possible from everything from the quantum computation and take into account environmental degrees of freedom. And exactly this treatment, that we leave out the coherence in the environment and in the leaked levels, allows us to make a very efficient simulation and tracking of these non-computational excursions out of the qubit Hilbert space using stochastic trajectories. And so that's the first step. So that's XPauli, which has proven to be a powerful tool. And I will show you actually in a few slides what it can do. So furthermore, we have also included here near-Clifford samplers that address the challenge of coherent over-rotation. So if you have a qubit, even a simple qubit, and you drive it by a laser or by a microwave field, and you try and implement a rotation like a pi rotation, so a sigma z or sigma x operation, then you will typically have the problem that your intensity of your control field is not quite perfect, and so you may over-rotate or under-rotate. And in some cases, this might be random, and in other cases, it might be systematic. And in particular, if you have this systematic over-under rotation, then actually errors can accumulate coherently. And this can actually lead to a significant enhancement in the effective error rate. And it's a little bit like in a quantum sensor where we use the fact that coherent signals in a system are accumulated more rapidly than a classical random signal, an incoherent signal. And so this is an important problem that we have to address. And a typical approach would be to kind of randomize these errors by twirling and get rid of this coherence. But as I sort of hinted at already, this might be a challenge because it may not be very accurate. And so here we take a different approach, namely that we use an observation that has been made quite a long time ago in a way, that every channel can actually be written as a signed sum of Clifford channels, but of course now not only with positive signs, but also with negative signs. So it's not immediately straightforward to sample from it, but you can actually design a new sampling algorithm that takes account of these signs and does a kind of classical sampling from this generalized probability distribution. This comes at a cost because the cost actually, the more, let's say, the larger the coherent errors are, the more non-Clifford this whole thing is. So therefore, the more negative some of the weights in this signed representation are, and the more complex the sampling becomes. But nevertheless, it has a major advantage because if we would do an exact simulation, we would have an exponentially growing memory. So now we reduce the memory, but we pay with an increased simulation time, which is often much easier to take care of than an enormous memory. And so I will not go into the technical details. We can discuss this later on. What I want to show you now is that there are some application cases which really show that for realistic noise, these kind of treatments are accurate, but standard Pauli noise treatments that are approximate fail significantly. Here is an example where we consider the same physical channel, but we describe it at different levels of approximation. And as a result, we will get very different predictions for the logical error rate. And the first thing I want to show you is simply coherent over-rotation in a qubit. So we can treat this by Pauli twirling, and then treat it using a Clifford algorithm. And here in this particular setting, we will then find that there's a logical error probability of about 18% for a certain set of noise rate and over-rotation angle and so on. And then we can use Plaquette at the near-Clifford simulator in Plaquette to actually treat this setting again using this advanced sampling algorithm. And we will find a much larger logical error probability of about 39%. And of course, we don't know which one is correct. And therefore, we compared it for reference to a full state simulation, which does not make any approximations. And there we find that within the error bars, the logical error probability is about 38.7%. So that's consistent with what we find in the near-Clifford simulator, and wildly inconsistent with the Clifford treatment, so after twirling. So it is quite clear here that the near-Clifford simulator delivers an accurate result, while twirling does not. The same one can do using leakage. And here, of course, we apply XPauli of Plaquette. And again, we make a very similar observation. If you treat leakage by deriving an effective error model that can be treated by Pauli noise, then you can actually see that it vastly underestimates the effective full state error rate, while XPauli can actually, again, reproduce very accurately what the full state simulator achieves. And so that shows that at a moderately increased computational cost, we obtain very much more accurate results. And we learn that really the treatment of these type of errors by Pauli twirling is not accurate. And of course, one can now always say we can try and tweak the approximate description, increase or decrease effective error rates, but this is something that we would then have to, in every instance, validate by some other method, either a full state method or in fact the near-Clifford or the XPauli simulator. And so therefore, this is really an indication of the importance that a fast simulation tool is useful only when the approximations that it makes really preserves the limiting hardware physics. And XPauli and near-Clifford do this to a much better extent than reduction by Pauli twirling. Okay, so now how do we go about this? I mean, what is kind of the flow in Plaquette? So the first thing you always have to do is you have to, of course, present the physical error model and the propagators for the evolution. And so you do this at the very beginning. And this is defined once. And from then on, this is used internally and converted internally to be adapted to the samplers and decoders that you choose afterwards. And so, of course, there's a whole range of samplers implemented in Plaquette. So you can see STIM, XPauli, near-Clifford, full state. You can choose them to then carry out simulations together with the suitable decoders. And in this way, obtain, for example, runs over many code distances for different parameters to determine thresholds, as an example. And so this is really what you then get out after sufficiently many runs. You can actually determine error thresholds. You can determine whether you're outside or inside. And you can then also play with the sensitivities. So you change physical parameters and you observe how it changes the logical error rate. And in this way, learn what is relevant on the physical level and what is less relevant. What is a hardware problem that you may want to address urgently, and which ones that might be delayed because they doesn't have such a strong impact on the logical error rate. And so this really guides then the development effort of a hardware maker. And there's a whole range of quantities that Plaquette will deliver. So this might be the threshold level itself, the logical error rate that you may have, error budgets, the suppression factor when you move away from the error threshold. And that means when you, for example, make the code larger and therefore go deeper and deeper, you reduce the effective logical error rate. This will improve the logical error rate very slowly when you are very close to the threshold, and it improves it very fast when you are very far from the threshold. And these sort of things you can learn from the system. Okay, so now let me give you 3 examples, real-world examples, from 3 different technologies. One is the Transmon qubit, a superconducting qubit that, of course, is a very important physical qubit that has seen a lot of considerable achievements in early stage quantum computers. And one of the challenges in Transmon qubits is leakage. And that means that you have the logical qubit level 0 and 1. And then you have additional levels that are removed from those levels 0 and 1. There might be a nonlinearity, so they might be sort of non-resonant, but nevertheless, you may populate them to some extent. Also, if you have several transmon qubits, then for example, it might be that both of them are in the excited state, but that is energetically perhaps not so different from one of them being in the ground state and the other qubit being excited to the second excited level, which is outside of the qubit threshold, out of the qubit manifold. And so this is something that we have to describe. And so here again, we first take knowledge from the experiment, from the error models, the Hamiltonian that the experimentalist has sort of tomographied. And we may also do simulations to get estimates of error rates. And this is forming the input to create the error channel. And then we make a comparison of various models using XPauli, but also STIM, for example. And let's see what we find here. So here we get from Plaquette, first on the left-hand side, a comparison of 3 solvers on a very small repetition code here, distance 3, just to be able to simulate everything exactly as well. So here we have the full state simulation in gray. We have the XPauli simulation result in green, and you see that they really coincide very nicely. And then we apply again Pauli twirling, and we then use STIM, and we see that it systematically underestimates the error. Here in the top panel, top left panel, this is about a factor of 2, something like that. But very interesting now is that if you increase the code to a distance 9, now we have already are a bit challenged in using the full state simulator, but we can still compare XPauli and STIM. And we see that again, there's a difference, but don't be fooled. It looks almost the same. It is actually a much, much larger distance because this is a different logarithmic scale. And in fact, this is almost, well, a factor of 50 or so in error now. So this is a much larger distance. So actually even the mismatch between the Pauli twirling result and the XPauli result grows. And we have all the confidence here that XPauli is accurate, while the twirling is not. Now, here on the right-hand side, you can see, okay, on one hand, one thing is the logical error probability, but it would also be interesting to see what it does actually to the error threshold. So we really ran now simulations using XPauli to determine the error threshold and also to use the Pauli twirl. And here we had a model. We needed 1 parameter, so we have dephasing noise, we have heating, and oh, there's a typo, there should be cooling, the third one. And we all parameterize them by 1 factor, so we scale them by the same factor. Simply, this is for simplicity to make a nice one-dimensional plot here. And what we see is a very big difference between the error threshold. So it's not only that there's a difference in the level of logical error, but it's also the position of the threshold that changes. And here, the mismatch is about 20%. So instead of 1.48% error threshold here, or gamma is 1.48. And a Pauli twirling, the prediction is 1.77, which is considerably larger. And so this is important information for an experimentalist. This is an example. There might be larger or smaller differences, but it's really important that XPauli is a tool that can predict more precisely what these quantities are. Okay, so another example, and that's neutral atoms. And so this also is serving to highlight that Plaquette is really hardware agnostic. We have superconducting qubits, neutral atoms, trapped ions. We can do photonics. There's many, many different settings, but here is the neutral atom setting. And again, we want to look at threshold surfaces. And again, in neutral atoms, an important aspect is this scattering from non-resonant levels. So you're typically trying to create Rydberg blockades and so on using some desirable of resonant Rydberg states, but you also will have other states that you might be coupling to a little bit that may scatter, and this you have to take into account because it is an additional error source that is actually can be quite important, because the faster you drive this system, the more you will have scattering errors. So you have to really take it a very accurate answer what their impact is, because this will determine to some extent how fast you will run your quantum gates. Okay, so here we did a simulation where we had dephasing and depolarization errors. And in addition, we had the scattering error. And for each one of these combinations, we try to determine what is the error threshold. And you can see here a reddish and a greenish pattern. And again, so that you can either treat this scattering error by twirling using Clifford algorithm, or you use XPauli. And you can see that the difference is very significant if you have so the level of scattering that they can tolerate, or that lets you sit on the threshold, can be very different under these two treatments. In fact, you can see here that it can be up to a factor of 2.6. This is important information because if I can, for some reason, if I realize that I'm much more sensitive to these scattering errors, I typically have to reduce, either I have to increase the detuning to these undesirable levels, or I have to reduce the intensity by which I drive the system. That slows me down. So it's very important design information to know about this. So finally, as another example, another hardware case. So here we have trapped ions. There are, of course, wonderful achievements in trapped ions. One of the first ideas for building a quantum computer came within the trapped ion arena. And one approach is that you trap several ions in this ion trap and then run quantum gates. That means you shine lasers onto the system, and you might also scatter a little bit of light, and you use the vibrational mode to provide a bus that connects different ions. And of course, your gates are not perfect. So the first gate might leave a little trace in your vibrational mode. The next gate, yet again, leaves a trace. And so if you run your quantum gates, one after the other, your motion will typically be perturbed more and more. The higher the motional excitation, the larger actually the error in quantum gates in such an ion trap quantum computer. So with increasing time, your error rate will actually evolve and typically increase. And it's a very important piece of information how long this can go on until your gates are really below the error threshold. And then you have to recool if you reach this point, and recooling is a costly point, a costly action, and you don't want to have to do this too often, perhaps. And so therefore, again, this is very important information to be able to treat this time-evolving error rate and learn how it affects the threshold. So here, again, we can now use XPauli to treat this system. And of course, we have the electronic degrees of freedom. We have the vibrational modes. There might be different vibrational excitations. The mode might be in ground state, 0, 1 phonon, 2 phonons, 3 phonons, and so on. And for every phonon occupation, we will have a slightly different error rate or even slightly different error model. And so we have to track this, and this we can do very efficiently using XPauli in Plaquette, and we can drive forward the simulations and then actually again find information about the error threshold, about the logical errors that you observe, when you perhaps should recool, how far you can drive this, how fast you can make your gates, because the faster they are, typically the more trace they leave in the vibrational mode. All these things can be learned from that. And so this is therefore also a nice framework to treat time-evolving error models. Okay, so to wrap this up, so we will really, we will have a workflow here. We build an error model, we run samplers, we decode, we analyze what these samplers are telling us, and then from that we can identify limiting physical factors in the simulation, in the hardware rather. We can estimate overheads that we need to achieve a certain logical error rates. And based on all this information, we can improve the hardware. And we can also decide which aspect of the hardware we will improve the first. And this will, of course, help hardware designers to decide what to do next. And therefore, progress more rapidly and also potentially reduce costs. So useful outputs here are really many quantities, threshold margins, error budgets, suppression factors, all these sort of things that are relevant to make these judgment calls in the lower half of this call. Okay, so let's close. And so really, we have here a setting that we go from device physics to logical performance and then to hardware priorities. And Plaquette is really a reliable, efficient FTQC simulation design framework that really treats real-world errors as accurately as is perhaps possible. And we have to give it, of course, initial information about the hardware encoded in error models. Then we choose the right sort of samplers, the right sort of degree of approximation to be sufficiently fast but accurate at the same time. And we can also compare these different levels. And we use all this information that we get to really take design information from the logical error rates, threshold surfaces, and error budgets, and so on that we learn. And so this really helps us answer the optimization challenge and in hardware design. Namely, it really determines what is the impact of real-world imperfections on our performance, and it gives guidance on which of these imperfections to work on most urgently. And so with this small overview of what is Plaquette and what are its properties, I would like to close. So of course, I have been not very mathematical for a theoretical physicist for sure. There's much more detail in our archive paper. And of course, I'm also happy to discuss now with you whichever questions you may have. Thank you.
Thank you so much, Martin. That was really, really nice. So yeah, let's open it up for questions. Anyone would like to kick it off?
I have a question.
Mm-hmm.
How do you actually build a noise model faithful to a specific piece of hardware? Where do the number came from? How do you know the model you end up with in Plaquette is the right one?
Mm-hmm. Right. Of course, that's a very valid question indeed. I mean, and to some extent, we depend here also on experiments. So there are different ways in determining your error model. So we represent it typically either by Krauss operators, or we can also give propagators. And we obtain this either by simulation. So we may know properties of the physical hardware. We can use simulation to determine an error model that is relevant. We can also, of course, work with the experimental, or the experimentalist that uses Plaquette can take information that he or she has about its hardware, for example, through process tomography, where they tomographied the noise and then write the model for the noise, and then implement it in Plaquette, run it, and see whether the output of these simulations, for example, with the exact state simulator, matches some predictions that bring some predictions that can then be verified in experiments. So that's what a hardware maker would perhaps do. And we as theoreticians, we would of course be able to have to build models and then compare those to available information about the experiment. Yeah, but the representation in the end, so the basic input into Plaquette will be Krauss operators on the one hand, or propagators, or transition maps and so on that are obtained from experiments.
Thank you so much for answering my question.
My pleasure.
So I actually did have a question too. I wonder if you can go back. I think it was the one of the experimental examples, the one that says same physical channel.
Ah, okay, yeah, this one.
Yeah, this one. Yeah, so this was really cool that you were comparing the near-Clifford to full state and XPauli to full state. And so there were kind of different channels, and then the simulator that did as well as full state was a different one, either near-Clifford or XPauli. So does Plaquette actually know which one is going to be the optimal one to choose, like the near-Clifford or XPauli, or is this something you have to kind of
Yeah, this is a very, very good point. I mean, of course, it will be dictated by different requirements. So if you want to be very accurate, of course, the very best you can do is a full state simulation. Probably the next best is near-Clifford or XPauli. And then further down the line, you use perhaps a stim with the Pauli twirl. But the question is also cost. I mean, the more approximations you introduce, the faster your simulations will be, but the larger the error. And it may well be that at the beginning you would make a quick and dirty simulation, so to speak, with large approximations, but very fast to get a first feeling. But then if you really want to understand what's going on and you want to be more quantitative, then you would move, for example, from Clifford to XPauli. A bit more, takes a bit more time, but will be more accurate. And so I guess there will always be this interplay here. And you can see this, I mean, if you have, of course, if you would have an error correction code with let's say 30 or 40 qubits, you would have an enormous challenge to simulate this with a full state simulator. It would take almost forever, even if you use tensor networks or so. It quickly becomes impossible even. And then you have to go a step further down. And at some point, also XPauli will, I mean, it can, of course, treat hundreds of qubits or even more, but at some point, it will also find its challenge and you have to go further down, for example. Yeah. On the other hand, I mean, if your STIM simulation gives you a threshold where you would say, this is unlikely to be true for whatever experience reason, then you have to do these tools. So requires a little bit of experience. But the good thing in Plaquette is you can do these changes very easily. All these are backends. I mean, you can choose them. You give once the error model, you can choose the simulator, the sampler that you want to use. And it's not much extra work, I would say. It's mostly waiting then for the simulation results. And so this is, of course, a big advantage over having to getting used to another simulation environment again, trying to use this to do your simulations.
Thank you again, Martin, and thank you everyone for joining us. It was really great. The recording is going to be available, so we'll send it out to everyone who signed up for this. And yeah, I'll call this to a close.